Okay. All right. So let's get back to this paper. Okay. So this is the parameter of interest here for a given. It's just like Callaway Santana's group time ATT. It's the for a given group. You know the. Let's just compare it with Callaway Santana since we did it. Here's there, right? For a G, that's the E of the other one. For the E, this y1 minus y0. This is going to be, because it's in event time, they're going to, well, not just because it's in event time, just they're going to say y1 minus y0 had they not been treated. But this is basically y1 minus y0. They just use the switching equation to go ahead and assume that it's y. All right. So we're going to have y1 minus y0. And for that particular group, they're going to call this the cohort average treated on the treated. And then they're going to introduce assumptions. So now what we're doing is we're going into identification. Well, we were I think this is still a part of the identification stage, the definition of the parameter. And then although I sometimes struggle with like what exactly these econometricians mean by each of these various steps, but there's this defining of the parameter that goes first, and then there is this laying out of assumptions, identifying assumptions. And the identifying assumptions, this is usually the identification stage. Sometimes applied microeconomists will describe identification as the consistent estimate of the point estimate, but econometricians seem to, if I understand correctly, they're describing the identification stage as laying out the parameter and then laying out the assumptions. I could be wrong, but that's what it seems like they're doing. So here we have this identifying assumption. Let's just call it that. So assumption one is a parallel trends assumption in baseline outcomes, and it's basically saying that for all units, for all cohorts, that absent the treatment, the units would have continued to evolve the same way. So here's the had they not been treated at period T relative to period S, they would have, that they would have not been, that their trends would have evolved the same. They make this interesting comment. They say never treated units might be different from the ever treated units. Think of it as a Roy model. What does it imply that they chose not to get treated? It may, think about it from like the perspective of a person that goes to college versus someone that never goes to college, right? It could be they face liquidity constraints. Could be they have preferences. Could be that even with the same liquidity constraints, they think that their options are better doing something else, right? It could be any of those. It could be any of those things. They couldn't afford to go to college. They didn't want to go to college. They have better options. So if they're a never treated unit, what does it imply that they chose not to get treated? What does it imply that they chose not to get treated? It may imply net negative treatment effects. They think that if they go to college, they will be worse off. Net on net. And that could mean that they do not have parallel trends. They may not share the same evolution of baseline outcomes as the treatment groups. So Sun and Abraham made this comment, and they said, if you think you're unlikely to satisfy the parallel trends assumption, then drop them. Just drop those units. I'm not saying to do it. I'm just pointing out that they say it. Grasshopper says, are those identifying assumptions easily translatable to causal graphs? I don't think they are, Grasshopper. I don't think they're very easy to put into causal graphs. Partly partly I don't think they're very easy because I don't know how to do them. I've got a panel graph showing showing what's needed for a two-way fixed effects estimator, but I don't know the causal graph for diff and diff that would illustrate parallel trends. Not saying you can't do it. People are able to do a lot with those causal graphs, but it requires a level of creativity that I've not invested in doing it. I've tended to focus on these. Potential outcome representations, but yeah, maybe somebody could. I don't know how to do it. What they're about to do, though, is they're about to lay out 3 identifying assumptions. And they're going to show, what they're going to do is they're going to show that mu coefficient, that population regression coefficient. They're going to show it, the mu, under different scenarios. They're going to show the mu under different scenarios with only some of these assumptions. That's what they're going to do. They're going to say, well, what is that coefficient equal if I only have assumption 1, if I only have assumption 2, if I only have assumption 3, if I only have 1 and 2, if I only have 2 and 3, if I only have 1 and 3, if I have all 3. That's what they're going to do. They're going to say, like, well, what is it I lose when I lose one of these? All right. So here's the second one. No anticipation. No anticipation basically means that in the pre-treatment period, there is no treatment effect. So it would be like this here, right? 1982 for the 1986 cohort, which is 4 years prior to treatment. What's the treatment effect, right? Well, how could there be a treatment effect in 1982 if the treatment hasn't happened yet? If the only way it could happen is if they know in 4 years there is going to be a treatment and they begin to change their behavior, right? And that kind of stuff does happen. Insofar as, I mean, that should be really natural to an economist, actually, who have these forward-looking agents. So if they know treatment is coming, they may change their behavior. They may not, though. I mean, they may not, like if you know there's going to be a gun reform in 2 years and you're a criminal, what are you going to do in T-2? How are you really going to change your life? So it kind of depends on a case-by-case basis. I have this paper that I think is going to be forthcoming. It was conditionally accepted about 3 weeks ago at a journal. And we look at the rollout of Craigslist's erotic services. I got an email here. No, I don't. We looked at the rollout of Craigslist's erotic services, which was like this section of the website that was used by sex workers to advertise to clients. And no anticipation actually holds. And the reason that it holds is because I'll show you how we figured out that it held. www.wikipedia. Is wikipedia.org? Craigslist. Advertising. None. They do no advertising. Craigslist does no advertising whatsoever. When they would open up in cities, when they would like open up a new erotic services in a city, because they like would roll it out at different points in time, there was no announcement. Nobody knew it was coming. So it was impossible that there be a treatment effect of you. That's different than trends. There's no way for there to be a treatment effect in 1982 if it's opening in 1986, because nobody knew it was opening in 1986. So that's what this assumption 2 means. No anticipation behavior. And if there's no anticipation behavior, it means that the average treatment on the treated is 0 for that period. Basically means that the potential outcomes prior to treatment at baseline are on average the same. This means there's no pre-trends, essentially. That's how I wrote up the slide. Um, I think that if you have parallel trends, you have no pre-trends. If you have no anticipation in parallel trends, then essentially the data generating process is just some kind of stochastic error term plus some fixed effects, and then therefore there's no by mechanically there's no treatment effects. There's no trends. There's no pre-treatment trends. So no anticipation holds. Sorry. So if there's no anticipation, then they can't deviate from trend in the pre-treatment period if you've got parallel trends. And then there's treatment effect homogeneity, and all that means is this. That means for the 1986 group, the treatment effect here, let's say it's right here, 1989, let's say that that's a 30. So 3 years after treatment, let's say that the treatment effect was 30. We need for the treatment effect in the +3, so these are our treatment dates here. So you've got a +3 period for 1986. I need to have if it's a 30 for 1986, I need it to be a 30 for 1992 in its +3 period. I need it to be a 30 for 98 in the +3 period. I need it to be a 30 for 04 in the +3 period. Okay. So if you have it be 30 for 1986 and then 50 for another year and then 100 for another year, then you have treatment effect heterogeneity. And that violates assumption 3. That violates assumption 3 because what it means is that cohorts are experiencing different paths of treatment effects. So cohort, that can happen. There's different ways for us to think about, if we want to think deeply about why that's happening, it could just be that the covariates are different and those covariates are interacting with the treatment. It could be like, compositional changes in the panel unit. So there's maybe waves of immigration that are happening in some of the panel units, and as a result of that, maybe the treatment isn't even open to those people. There can be all kinds of stuff like that. It doesn't rule out parallel trends is the point. It doesn't rule out parallel trends. Trends can be different. I think I have here picture. Yeah. So I've got here a picture. Let's see, do I have? Yeah. So look at this. So this is a picture of heterogeneous treatment effects by different groups. So notice here we have pre-trends being 0, but in group 1, you've got this slope that looks like this. These are dynamic treatment effects here. These are actually not as steep. So it's hard to visualize that they're not as steep, but this actually has a slope of 10. This has a slope of 8, and I think this has a slope of 6. Okay, but you can't really, it looks like this one's steeper, but that's because the y-axis is shortened. So it's actually flatter. So this is the steepest. This is actually flatter. If it was on a 150 scale, you would see it flattening. Okay, so notice though, we have treatment effect heterogeneity, but parallel trends actually does hold mechanically. It does hold. You can't visualize it here, but actually, you can sort of take my word for it. This is the pre-trends. They're 0. They would have been 0 over here absent the treatment too. So treatment effect heterogeneity doesn't violate parallel trends. Okay. So this is the two-way fixed effects regression. This is essentially here, the differential timing regression. It's just going to be regressing y onto the treatment dummy with fixed effects. So that right there, this right here is the static regression. So, well, no, actually, the absorbing state. Oh no, yeah, this is the mu g. This is everything. Okay, so these are the sum of all coefficients. All right, so this is going to be basically every single lead and lag. And we're interested in the properties of mu g. This is what we want to know. What is mu g under differential timing, as well as whether there are any never treated units. Okay. All right, so this is the easier one. This right here is the static specification. I prefer to write it this way, but they wrote it this way. Okay, so this is the static specification, and this is the dynamic specification. You've got mu L going for the pretreatment period, which would be this. This would be, the -1, -2, -3, but it would be the -1, -2, -3 for all the groups, okay? So it would be like mu L would be describing a -2 group, okay? So that or a -6 group. So that would be the coefficient associated with all 4 years, okay? So the first thing we learned from this paper that I don't think we knew was that when you're estimating event studies, you've got 2 sources of collinearity that you have to contend with. One is that you can't estimate every single coefficient. You can't estimate every coefficient because of the dummy variable trap, as they call it. Because of perfect multicollinearity, you can't invert the matrix. It's got to be you've got to drop something. You've got to drop one of the variables. So here I drop the -1, and this should actually be -2 going to -k. Sorry about that. You drop the -1, and that one we kind of knew. So you could see it over here with Miller. They always drop -1, right? They always drop -1 in this simple 2x2 thing. But the thing that was, you see in 2 papers, you see it both in Sun and Abraham, and you saw it in Borisak's et al. Paper, is you also have a second form of multicollinearity with differential timing, and that is to achieve balance in the differential timing. You've got multicollinearity coming from this linear relationship between 2A fixed effects and the relative period indicators. So you actually have to drop 2 variables. And so you would drop -1, the baseline, and you might drop like -4. This is recommended if you're doing 2A fixed effects. Secondly is we have some terms here, trimming and binning. I do both in the mixtape when analyzing Ching and Hoekstra. Binning means placing all distant relative time indicators into a single dummy. That's what binning means. We did it just a second ago. Remember when we were doing this binning? Oh shoot! Right here where we were doing tab bin before. We were like tab time till if bin before equal 1. And we were like, oh, binning means sticking all of those excess leads into one dummy. And the reason you do it is because now if I was to estimate a model that went from, that estimated all these leads here, I would go DD -1, -2, -3, -4, -5, bin before. 1, 2, 3, 4, bin after. Okay, so it's what it does is it guarantees that what it basically does is it groups together everybody into the same, since the only way I could ever calculate a coefficient on -24 would be to use the last group treated, and there'd only be 1 unit in the treatment group. But if I was to use, if I was to try to identify the -5 coefficient, well, I would be using all 4 states. See, look, trab treat date if time till equal -5. I'd be using all 5 states. But once I get to tab treat date if time till equal -7, I only use 3. So you're getting, you're actually, what's happening? When you try to estimate all the coefficients, you're getting imbalance in relative time. You're losing states in relative time. It's weird because the data structure is still that perfect square, but or rectangle. But when you're moving it into relative time, it's now imbalanced in relative time. And so people will typically do one of 2 things. They'll bend. In my mixtape, I show both of them. They'll bend, which means placing all distant relative time indicators into a single dummy. So you can bend them. And the other is you just drop them. And you just like impose balance through dropping. And so what would that mean? That would mean this. Drop if time till less than equal to or less than -6. Drop if time till greater than 5. Okay, now I've got balance in relative time, but look, I've got imbalance in calendar time because I've only got 250 observations for the pre-1986, and I've only got 250 observations for that. But in terms of relative time, it's perfectly balanced. And I did that through trimming. So trimming means excluding any relative period for which you don't have balance in relative time. And this is going to create a balanced panel in relative time, but it's going to be an imbalanced panel length overall. So you can kind of see this. TS set ID year. XT describe. Right? So it's imbalanced now in panel calendar time. But it's balanced in relative time. It's kind of a new thing for me. This was not something that I was really thinking about when I was doing these differential timing. But other people were. You see it in Mark Anderson's paper when they make this plot. They appear to be bending. They appear to be dropping, trimming. Okay, so a lot of people were doing it. You see it. A lot of people were doing it, but I never really thought about it. What I did usually was bend, and that was mainly aesthetic. I did it mainly for aesthetic reasons. So they're gonna analyze both in this example, and they're gonna see how it affects mu hat. So this is the what the coefficient mu g. All right, that's the bend coefficient. What is mu g actually? So when I estimate it, all right, when I estimate mu g, all right, what exactly am I estimating? What exactly am I estimating? And mu g is, this is just the number. This is the decomposition. Okay, this is the decomposition, not in terms of causal parameters, but just the decomposition. And what you get is 2 by 2s here. Okay, so you get this 2 by 2 here, yi minus y, untreated for the treatment group, and then this is for an untreated group. So you get difference, 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 and difference. So there's like a difference, 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 and difference for that particular period. So it's for the units in that bin. Okay, then you've got actually mu g is equal to difference in difference terms from other periods. Okay, so that would be this here. So this particular coefficient is based on the difference in difference for that period. Okay, but it's also based on a difference in difference from this period. Now I'm not saying this coefficient, this coefficient has already done it. Okay, but what I'm basically saying is this contains a difference in difference from this period and from all other periods. and it's going to contain a difference in difference that would have occurred in the omitted period. Here. So you got this other relative time diff and diff, and you got this other excluded time diff and diff. So you got three things that are going into every single one of those coefficients. The unique diff and diff for that period, the unique diff and diffs from other periods that are in the here. So it's like, you know, all the negative k to negative 2 is the other. And then also for the negative 1 that's not even in there, the dropped group. Okay. So this was my cheat sheet I had to make. For relative periods of mu g, you got these weights here. See these weights? Weight, weight, weight. There's three kinds of weights. Okay. So for relative periods of mu g's own weights, the weights sum to 1. So that would be like for the negative 1 periods for the 4 different groups, which we saw right here. So tab, treat, date, if, time, till equal negative 1. All right. So you've got these weights sum to 1. The weights associated with negative 1 coming from 4 different cohorts. Okay. Those weights might be 0.25, 0.25, 0.25, 0.25. They're going to sum to 1. So the relative periods of mu g's own, they're going to sum to 1. The relative periods belonging to some other bin, right? So this is like for negative 1. There could, in that coefficient that goes with negative 1, right? It's equal to the weighted average of these 2x2s. It's equal to the weighted average of other periods, not for negative 1. So for like negative 2, for 0, for other periods, that is gonna, those weights are gonna sum to 0. So these weights sum to 0. These weights sum to 1. These weights sum to 0. And these last weights sum to negative 1 for relative periods not included in G. So that would be the negative 1. See how negative, it goes 0. I gotta fix this. To negative 2. We've skipped negative 1. The weights on the omitted groups. So there would be like, you know, there would be, remember how we said right here with this multicollinearity, you would drop two leads. The weights from there sum to negative 1. Okay, the weights from those 2 dropped ones sum to negative 1. All right, here we go. Yeah. So you can estimate the weights themselves by regressing the treatment variable onto bin indicators. That would mean like, that would mean this right here. This would be our bin indicators, dummies for every single one of these. Okay, done bin, you know, for the bins. This is for trimming, but look what I did, the bin before, bin after. Keep thinking I'm saying Ben Affleck. All bin indicators included. All bin indicators. So it's going to be you're gonna regress it onto the bin indicators and the leads and lags. Yeah, and then the unit and time fixed effects. Okay, that's how you get the weights if you wanted to get them. All right. So let's interpret the coefficient under each of those 3 assumptions as well as combinations of those assumptions. So under proposition 2, under the parallel trends assumption, the population regression coefficient on the indicator for relative period bin G. All right. So what is that? That would be for the, I run the regression. I kind of have some examples here where I run these regressions. So here's like regression of DD1. What is DD1? Tab time till if DD1 equal 1. Oh, I deleted it already. Shoot. Tab time till if DD20 equal 1. Yeah. So that's the negative 5. The negative 5 period. So under the parallel trends assumption, okay, what does the coefficient on negative 5 mean? It is the weighted average of the cohort average treatment on the treated for negative 5. So that would be like, what is the cohort average treated on the treated for the negative 5 period, right? plus the weighted average cohort average treated on the treated for other bins. All right, so that would mean, so if I want to know what the coefficient is on DD1, it's going to be the average treatment on the treated for DD1 and all these others. Or actually, it's going to be and this one, and this one. It's going to be the weighted average over all those, right? And those weights sum to 0, okay? And then the omitted one. What's the omitted one? Well, I omitted DD21 and DD24. So those DD21 and DD24 average treated on the treated are also in there. And that's why you can get weird pictures like this. Because this coefficient, even under parallel trends, this coefficient will contain the average treated on the treated for that period as well as all the others. These are not the average treated on the treated. These are the coefficients that are already contaminated. Right? That's what I'm saying. They're already contaminated. Whoops. They're already contaminated. This is the coefficient. This is the true value. And this coefficient is contaminated with these two additional things. Okay? Undesirable. All right? We don't like that. That's called proposition 2. What about parallel trends and no anticipation? That doesn't solve it either. All that you're getting from no anticipation is zeros on the cohort average treated on the treated for the pre-treatment period. So you still get here what you're looking for. This is what you want. And actually, this is kind of nice because look, those weights sum to 1. So they're like positively weighted averages, which is usually what people are wanting. Remember how, I don't know if you've noticed all the time they'll talk about these negative weights. You're not getting negative weights on the true average treated on the treated. You're getting them like over here and over here. And these other things. This is the non-convex combinations. So when you relax and you allow for no anticipation, you're losing the average treated on the treated for the pre-treatment period. Okay, so what that means is here, that would mean that average treated on the treated is now 0. That average treated on the treated is now 0. That average treated, average treated, average treated, average treated. Those are all zeros. But even then, imposing those zeros is not enough for this mu g to equal just this. That's what we want. We want mu g to equal the average treated on the treated for G, for the G period. That's what we would like. We would like the coefficient on -1 to equal the average treated on the treated for -1, but it doesn't. It equals average treated on the treated for -1 plus any other average treated on the treated outside of that's in the model, but not this. So the coefficient on -1 will equal the weighted average of -1. It will not equal the average treated on the treated for the -2 to 6, but it will equal the average treated on the treated from the other future periods. So that's the problem. It's hard to see it down here, but that's what this notation is telling you. Okay? And it will still equal the average treated on the treated for the omitted groups. Okay? So, what about proposition 4? What if you have parallel trends and treatment effect homogeneity? Okay, but you don't have no anticipation. Well, if you require treatment effect homogeneity, the main thing is you don't get the C anymore because there's no cohort specific average treated on the treated. There's just a T+1 average treated on the treated, a T+2 average treated on the treated. But that's still not enough. The no anticipation, this is not canceling out. This is not canceling out. So you're still getting all these other average treated from the other, the other pre-treatment periods that are so you're getting all of it. You're getting, so with this right here, what you're getting is, so for the -1, you're getting all of those. Well, let's say the omitted group was -1. Okay, let's say that was the -1. So then if you want to know what it is for -2, it's all of those weights that sum to 0, and that one. If we have parallel trends in relative time holds, aren't we back to the classic diff and diff? Yeah, but the parallel trends is not in relative time. It's in calendar time, I think. Let me look again. I'm pretty sure it's in. It's supposed to be in. Yeah, see how it's measured in. See grasshopper. It's in the letter T. So that's having to do with calendar time. I actually created in the Baker data set here. Look at this Baker data set. So we generated a variable called Y2, and it was based on a firm fixed effect with a linear time trend plus some error term. If this was 0, if there was no treatment, then everything would grow at some same trend. They would grow at some N, and then they would grow at some E. So parallel trends has to do with the calendar time, okay, not the relative time. So we're not assuming parallel trends in relative time. Okay. That's why it's called parallel trends in baseline. Hey Toba. Here. So if you have parallel trends and treatment effect heterogeneity, right? Then you get parallel trends gets you to causal effects. That's why I notice how once we impose parallel trends, so this is it without any assumptions. It's just a bunch of numbers combined to give you a coefficient here. And once we impose parallel trends, we get causal parameters. Parallel trends gets you to causal parameters. Okay, they just end up being contaminated. The coefficient ends up being contaminated with other causal parameters. All right. If you get parallel trends and treatment effect heterogeneity, but you don't assume no anticipation, you're getting all this no anticipation contamination. This is the no anticipation contamination, or this is the -1 to -6 anticipation, and this is the omitted group. Okay. So many propose binning or trimming. Son and Abraham note that binning creates uninterpretable weights, whereas trimming creates weights that are more reasonable. And that's because when you trim, meaning dropping, which is what we did right here, we trimmed when I said drop if time till greater than 5, drop if time till less than 6. Right? What that's doing is it's just getting rid of those particular periods, CATT. Just getting rid of it. All right, so let's look at all this kind of notation is hard to work with. So let's just look at a toy example. We're going to look at a balanced panel, 2 periods. It's going to go from, we're going to have cohorts E and I. They're going to be cohorts 1 and 2. We're going to drop 2 relative time periods to avoid multicollinearity. So we're going to drop, we're going to include the -2 period, and we're going to drop -1 and 1, right? We're going to drop those 2 periods. When we're estimating the regression model on -2, so that would be right here, okay? We're estimating the regression coefficient on that -2 value. It's a dummy, equaling 1 if it's -2 and 0 otherwise. Remember, you're always getting the sum of 3 things, okay? You're getting the CATT for that period. You're getting the CAT, the weighted average of the CAT from the other bins. So that we said was the 1 and the 2. Okay, the 1 and the 2. Actually, in the no, sorry, -2 here. Sorry, I forgot which one was which. So we got the -2 CATT, and then we've got, because we're including the 0, all right, we're getting the CATTs for the 0 period. All right, we're getting the CATT for the 0 period. But remember, the weights sum to 0 for this period. So you get 1/2 plus 1/2. Sorry, 1/2 plus -1/2 summing to 0. All right, and then we get the we're leaving out -1 and 1. All right, we're doing what they said, which was drop 2 relative time indicators, and you get these. Look at these weights; they're summing to -1. 1/2 minus 1/2 is 0. Minus 1 is -1. Right, and so what you get from that are the CATTs from that period, which is the 1 and the -1s. Because look, here's the omitted groups. We're actually dropping from the post-treatment period, and we're dropping from the pre-treatment period. And you can just see here, we're getting contamination. So the only way that these will drop out is if we have no anticipation. No anticipation, we'll call those to disappear. Right, because CATT will be equal to 0 for the pre-treatment period. So no anticipation always eliminates the pre-treatment CATTs. Okay, but we're gonna lose. This is the excluded periods. Okay, the excluded periods, and these will only cancel out if you have homogeneous treatment effects, because what's going to happen is the sum of all these will be 0. All right, still leaves you. Well, actually, this will cancel out. So you get CATT will equal 0. Yeah, that's this. What did I say here? Chose to exclude a group with a treatment effect. Oh yeah, this is a post-treatment effect here. 1/2. So this should be -1 minus 1/2. Something doesn't feel right. I think this one and this one are canceling out. And then this one and this one should be canceling out. Still leaves us, and then this one will be canceling out. So still leave. I gotta look at this a little bit more. But I think that under those, yeah. Oh well, okay, sure. Under no anticipation, weights are not summing to -1. 1/2 minus 1/2 is 0. -1. Right? Jenny, isn't that right? So we get 1/2 minus 1/2 is a 0. And then we get the -1. So no anticipation is going to get rid of this. Homogeneity is going to get rid of. I still am a little. I think because I'm just staring at it and not noticing it, still leaves CATT 1/2. Second and third terms. I think that means this. Yes. Okay. My brain is not able to interpret my slide for some reason. This is going to be right here. No anticipation is going to eliminate that. and no anticipation should eliminate that. But it's still going to leave us with this, because this is a post-treatment. This is a post-treatment CATT, right? This is a post-treatment CATT because look, it's a 1. See, the problem was here we dropped a post-treatment period, right? And so as a result of dropping that post-treatment period, we leave this one in the coefficient. So, I mean, this is kind of, ridiculous, but you shouldn't be dropping for your comparison group a post-treatment period because its CATT will be contained in here. What I'm not seeing is how homogeneity is canceling out the second and third terms, except that, oh, yeah, I do. Yeah, I do. Duh. Second and third terms, because these are not the pre-treatment leads. That's what it is. Sorry. These are not the pre-treatment leads. This is the year of treatment, right? So there is a treatment effect in the year of treatment. But since they're the same, since they have the same treatment effect under average treatment on the treated, so this is group 1. This here is group 1. This is group 2. Okay? Then since they're the same, they sum, they cancel out. That's right. My bad. I'm glad I worked through that. I hope that made sense. I apologize. And then we lose all the no anticipation zeros. Well, there is no CATT in the -1 period, so that's gone. And there is no CATT for group 1 in the -1 period, so that's gone, leaving us just with this. Now look, see, that's not a negative number, so that has nothing to do with no anticipation. And you could have treatment homogeneity and get rid of that C, and it's still there. Well, why is it there? Because it is a dropped group in the post-treatment period, and homogeneity doesn't address that, and no anticipation doesn't address that, and parallel trends doesn't address that. But nobody's doing that anyway. Nobody's dropping a post-treatment period. Anyway, so that's where the contamination's coming from. So they propose an interaction weighted estimator, IW, as a consistent estimator for mu G. And here's the trick of it. It's not going to use, all of this problem here, this differential timing stuff, it was actually coming from using already treated units as controls. And if you can drop those and you can use untreated units as controls, then you can get around this through their interacted weighted estimator. And all that the interaction weighted estimator is going to do is it's going to use the last cohort treated as the control group for all of this. Whereas Callaway-Santana uses either never treated or not yet treated, Sun and Abraham are going to use the last cohort treated as the control. It's not going to have any covariates. They note that you could plug in Callaway-Santana, and then the interaction is going to be a two-way fixed effects regression specification that interacts relative period indicators. That would be these. That'd be those DDs that I made. Those relative time indicators with cohort group indicators. So what would that be? Whoops. That would be this is this. That'd be right here. Interact these with dummies for these. Okay? So you're going to interact your relative period indicators with cohort group indicators. You're going to exclude indicators for never treated cohorts or for last treated cohorts. So you're just going to go in steps. You're going to run that regression that I just said. You can use never treated or last treated cohorts. Drop the always treated. You're going to estimate the weights using sample shares. That's all that it's going to be. So for us, so yeah, you can see it actually right here. The 25% of the sample is 1986. 25% of the sample is 92. So the probability of being in the 1986 group is 0.25. Okay. And then you're going to take the weighted average. You're going to take those 0.25 times those coefficients, sum together, and that's going to be your mu hat. It's called Vhat. It's going to be the coefficient on So like rather than having this funky thing here, maybe it'll be at the 0. Maybe it'll be at the 0. Okay? You don't need treatment effect homogeneity anymore. You don't need treatment effect homogeneity. That's the great thing about their interaction weighted estimator. You no longer need treatment effect heterogeneity. You can have homogeneity. You can have heterogeneity. So under parallel trends and no anticipation, this delta hat is consistent. And sample shares are also consistent estimators for population. IW, not IV. IW is a consistent estimator for the weighted average of CATT. And now the weights are positive. Okay? The weights are positive. So you can see it here. All these weights are positive. No negative weights at all. And so they show that each IW estimator is asymptotically normal and they get its variance. That doesn't rely on the bootstrap. And if parallel trends and no anticipation hold, then the DD estimator using any pre-period and non-empty controls is an unbiased estimate of the CATT for that period, which would be unbiased estimate for this, unbiased estimate for this. And you're back doing event studies. You're just doing them correctly. Now, where is the software for doing this? I found it here. If you go to this, let me write this in here. See, it's github.com ASJADNAQVI/diff and diff notes. I think that'll take you there. Let's see. Oh, it should be GitHub. Sorry. I think that's it. Yeah, that's it. So you go to there. All right, you go there. And down here at the bottom, here it is. No, where is it? Here. No. Oh. Looks like Kyle actually made a single. That's weird. It looks like Kyle might have a single package. Oh, let's see. Let me look at that. Oh, that's the R package. So it looks like Kyle made an R package called DID2S that does everything. But let's look at this data. Here we go. Event Study Interact by Sun and Abraham. Here it is. You do this. You type in net install event study interact. You get it. Help event study. Oops. Interact. And then you've got the implements the interaction weighted IW estimator. And it'll give you, so it'll walk you through exactly what this does, but you'll have code that'll explain it. You can do it. All right. So let's take, I just spent 2 hours on Sun and Abraham. I just can't even believe that. So Bacon shows that the two-way fixed effects coefficient on the static parameter is contaminated by the other periods, leads, and lags. 3 strong assumptions are needed for two-way fixed effects. Stochastic Shock says, are these R packages and stated packages identical? I don't know. That's a good question. Stochastic Shock, I don't know if they are. I would probably, if it was me, I would probably use the package that the authors wrote. So this is the package by. So Sophie Sun wrote Event Study Interact. I would use it. The Chase Martin and DeHolfel wrote DID multiple GT. I would use that one. Borsak, etc. wrote DID imputation. I would use that one. Santana and Zhao. That's DRDID. I don't know. I might go down here and use the one that they wrote. Because if you can use the one the authors wrote, they have an incentive to kind of get all the bugs out. I would probably use that. You'd have to check the two and see how different they are. Okay, good. Okay, so the main thing is you don't, with the three-step interaction weighted estimator, you don't restrict the treatment effects to be homogeneous. They can be heterogeneous. Uh, so let's stop. Let's take a break. We'll come back at 10 minutes after. All right? We'll come back at 10 minutes after. And I apologize I'm taking so long. That's kind of the complaint that I have about my teaching is I seem to take a long time.